All right, guys, good morning. Again, it's always good morning. We're gonna continue with the review session. And I did problems until up to section 2.8. So let's continue with 2.9. And from 2.9, you're suggested to do problems 9. Let's see. 9, 31, 33, 35. Let's do one of those. Let's do maybe like 33, 35. Maybe we'll do let me see here. We'll do like 30. Let's just do 31. 31 says estimate 1.9999 to the power of 4. Okay, so the way I would ask you a linear estimate question is to begin by asking you to find the linear approximation of f of x. So this is a number raised to the power of 4. Maybe we could do a problem 33 because the derivative in 33 is a little bit more challenging, actually. 33 is the cube root of 1001. Okay, so yeah. So here the function is the cube root function. We're going to find the linear estimate of cube root of x. Okay, now 1001 is near 1000, and 1000 is a perfect cube, right? We could do the cube root of 1000. It's rational. So we're going to do the estimate of this at x equal to 1000. Okay, or they call it a equal to 1000. All right, so again, just look at the number and see what this is, the, what is the nearest perfect cube to the number that you're trying to estimate. It's 1000 because the cube root of 1000 is 10. Okay, anyway, I mean, I would ask you to I would tell you already which function and which a to use. So again, we know that if x, so again, this is the answer. If x is near a, then f of x can be estimated using the equation of the tangent line, which is f of a plus f prime of a times x minus a. Okay, so here our a is 1000. You want to begin by calculating f prime. Right, so here again, f of x is cube root of x, which you can write as x to the 1/3. Therefore, f prime of x is 1/3 x to the negative 2/3, which you could write as 1/3 times the cube root of, let me just write it as x to the positive 2/3. So now go ahead and find, you need to find f of a and f prime of a. Here is the function. So f of 1000 is just the cube root of 1000, which is 10. And f prime of 1000 is 1/3 times 1,000 to the power of 2/3. Okay, so to calculate 1,000 to the 2/3, you want to take the cube root and then square. Okay, so we get 1/3 times cube root of 1,000 is 10. Square that, you get 100. 1/300 is the derivative at 1,000. Okay, so we can now plug into the linear estimate formula. Cube root of x is approximately equal to let me just do this. It's approximately equal to f of 1,000 plus f prime of 1,000 times x minus 1,000. I'm just rewriting the formula with a being 1,000 right here. So plug in the values, you get 10 plus 1/300 times x minus 1,000. Okay, so if x is close to 1,000, then we could say cube root of x, which is a nonlinear function, is approximately 10 plus 1/300 times x minus 1,000. Okay, so this linear estimate works if your x is near 1,000. Now part B, we can go ahead and estimate the cube root of 1,000, 1,001. So all you have to do is plug 1,001 into your linear estimate. Okay. Because 1,001 is near 1,000. 10 plus 1/300 times 1,001 minus 1,000. Okay, so again, just replacing x with 1,001, and that's it. That's 10 plus 1/300. And that's it. 1 and 1/300. Okay. I mean, you could write that as a fraction, or you could write it as a mixed number if you want. I don't know. What is 1 divided by 300? That would be a 3. So it'll be 10.00333. Okay. It's a non-terminating thing. Basically, 1/3 is 0.33333, so on. So 1/300 is just add 2 zeros after decimal. Okay. But again, if you leave your answer like that, I'm not going to penalize you. Right, so linear estimates is a thing to know before moving on to calculus 2. Section 3.1 is on maximum, minimum, absolute max, absolute min, extreme value theorem, where you find the absolute max and min on a closed interval. And I asked you to do problems 51, 57, and 59, which I did last time. Yeah, I'm just trying to use my time wisely, but let's do one of those. Okay, let's do a problem. Maybe we'll do the trig problem. Okay, so our function here is f of t equal to 2 cosine t plus sine 2t. And the question is to find absolute min, max on the closed interval 0 to pi over 2. Okay. Yeah, this function is continuous. Cosine sine functions are continuous functions. So on a closed interval, this function is guaranteed to have an absolute min and an absolute max. All right, it is a guarantee that it is going to happen. Now, the absolute max min could happen at a critical value where the derivative is 0, or it could happen at those endpoints. So we need to find the derivative. F prime of t is equal to, and I know what to do next with this question. This would be a good question, actually. I might not ask you a absolute max min question like this one directly. I might ask you to, for instance, use this idea to find bounds for a definite integral. You know, I haven't asked one of those yet. I did not ask finding bounds, max min inequality for a definite integral. So on the final, I am likely to ask one of those. But again, max min can happen at the critical values. Take the derivative. The derivative of 2 cosine t is negative 2 sine t. And the derivative of sine 2t, so many people have forgotten chain rule on their third and the fourth exam. And I kept repeating, don't forget to take the derivative of the inside. But the derivative of sine u is cosine of u. U here is 2t, times that by the derivative of 2t, which is 2. And you could put 2 in front of cosine 2t. So chain rule on the second term. All right, now we need to set this equal to 0 and see when the function has a horizontal tangency where we could have a possible max min. Now, to solve this thing, you need to express the equation in terms of a single angle. This is sine of t, this is cosine of 2t. These are not consistent. We use a double angle identity for cosine to rewrite in terms of sine. Okay, this is a sine. We want this to be also in terms of sine. Okay, so we'll leave the negative 2 sine t alone, and cosine 2t with the 2 in front happens to be 1 minus 2 sine square t. Okay, so again, here we did the double angle ID for cosine of 2t being 1 minus 2 sine square t. There are 3 identities for double angle of cosine. I use this one, the one that has sine in it, because this equation has a sine. Okay, so what you can do here, guys, is to take this 2 out and just divide it out if you want, or you could keep it. But it's better to shrink the equation if you can. That's just negative sine t plus 1 minus 2 sine square t, all equals 0. So divide all by 2 is what we did to get rid of the 2. It's better also to factor out a negative because the leading coefficient, which is the coefficient of sine squared t, has to, it's better if that is a positive. It's easier to factor the equation. And write it in a descending order. Okay, please don't divide that negative out. Just actually you can if you want, you can ignore that negative. But I want to write it in a descending order with a positive leading coefficient. Factor this quadratic out. To get the 2 sine squared t, we need a 2 sine t and a sine t. To get negative 1, we need negative 1 and positive 1. Hopefully this factorization works. Multiply the outer terms, you get 2 sine t. The inner terms minus sine t, that gives you sine t. So this factorization works out. Okay, we have 2 factors that each equal to 0. This gives us sine of t equal to 1/2. And the second one gives you a sine t equal to -1. Okay, now we need to get the values of t. You don't need all of them. You only need the values that are on 0 to pi over 2. Okay, these have infinitely many solutions. We don't need all of them. Okay, so it's on 0 to pi over 2. What's going on here? All right, sine of t is equal to 1/2 when t is equal to pi over 6. Let me just see what's going on with this pen here. Hopefully the battery is not out. Actually, it's not. Okay, we also have a t equal to 5 pi over 6, which is not what we are concerned with. That's it. That's the only solution. 5 pi over 6 is not in that interval. And t is equal to -1 when t is 3 pi over 2. And again, we're not concerned with that either. So I'm writing those solutions, but I'm crossing those out. Thankfully, they're not in that interval. Okay, so now we are going to check for min and max on 0 to pi over 2. Plug in 0. Plug 0 into the function. The function again is 2 cosine t plus sine 2t. Let me copy down the function. Okay, so f of 0 is 2 cosine 0 plus sine of 2 times 0, 0. That gives us 2 sine of 0, 0. Cosine 0 is 1. F of pi over 6 is going to give us 2 cosine pi over 6 plus sine of twice of pi over 6 is pi over 3. Okay, so that's 2 times √3 over 2 plus sine of 60 degrees is √3 over 2. Okay, so that's root 3 plus root 3 over 2, which is, it's like having something plus half of that thing. That would be 3/2. So you got 3 root 3 over 2, or you could just leave the answer like that. Okay. So far, which is the bigger one? F of pi over 6. Okay. Is that right? Yeah. And then f of pi over 2, plug that in, you get 2 cosine pi over 2 plus sine of pi. Twice of pi over 2 is pi. Cosine pi over 2 is 0. Sine of pi is 0. So 0 right there. Okay. Yeah, and that is the absolute minimum. Absolute minimum of f is 0, which happens at x equal to pi over 2, and absolute max of f is 3 root 3 over 2, which happens at x equal to pi over 6. And I hope that the fear is gone, the fear of trigonometric equations by now. Okay, so what would be a good follow-up question? Again, using the max-min inequality. Okay, so let's just do that and get it out of the way. You're going to find bounds for the integral from 0 to pi over 2 of the function, which is 2 cosine t plus sine 2t. Okay, we are now finding the value of the integral. We actually can. We can find the value of the integral, but that's not what you're asked. You're asked to find bounds, and then we're going to actually find the integral and see if it's if the bounds are good. They should be good. Okay, so again, all you have to do, remember that that if you have a continuous function from a to b, okay, the integral of that function from a to b is always between the minimum, okay, little m is the minimum times the length of the interval, and the maximum times the length of the interval. Absolute min, capital M, absolute max. Okay, so since we have our little m and capital M from this last problem, then we can say that this integral is between little m, it was 0. Okay, the absolute min of f is 0. So 0 times pi over 2 minus 0, pi over 2 and 0 are the bounds of integration, or the endpoints of the interval, and the maximum was 3 root 3 over 2 times pi over 2 minus 0. Okay, so this integral is between 0 and 3 root 3 over 4. Yeah, I'm just gonna wait a little bit for everyone. to digest this information.
Should there be a pi on the 3 root 3 over 4?
Yeah, absolutely.
Okay.
Thank you so much. Mhm. Okay, so yeah, that's that. All right, that's the answer.
So would you pose a question like that on the exam as a continuation, like
Yes,
you did here? Okay.
yeah, I would. Yeah. So if you are in case to find the value of this integral, look, we do the max-min inequality for integrals that are not doable. And a lot of integrals out there are not doable. This integral can be done. Let's actually find the value of the integral. Using the fundamental theorem, we find the antiderivative, we plug in pi over to 0. Okay, so the antiderivative of, yeah, so first of all, 2 is a constant factor, leave it alone. The antiderivative of cosine t is sine t, guys, not negative sine t. The derivative of cosine t is negative sine t, but the antiderivative of cosine t is positive sine t. That's because when you take the derivative of sine t, you get cosine t. Okay, the antiderivative of sine 2t, this is not a direct integration, guys, because this is a composite function. The inner part is 2t. So you would have to do a substitution on that, okay? But I can let you guys use a shortcut for this kind of problem. Whenever you have sine of something t or cosine of something t, you would have to let u equal to at, okay? So if I let u equal to 2t, then du is 2, the derivative of t is 1, so 2 dt. Then I would have to divide by 2, get 1/2 du equal to dt, okay? dt gets replaced by 1/2. So the integral is going to have a, or the answer is going to have a 1/2 in front, 1/2. So we do plus 1/2. And again, the antiderivative of sine is negative cosine of 2t. Okay, minus. I'm going to put the minus in front of the whole thing. And then let this go from 0 to pi over 2. Let me write those shortcuts one more time. So again, the antiderivative of cosine, let's do sine, sine of at by substitution is negative 1 over a cosine of at. You could put 80 in parentheses plus some constant, and the antiderivative of likewise cosine of at is 1 over a sine of at. If we were to take the derivative, guys, the derivative of sine of at by chain rule would be cosine at times a. The derivative of at is a. If you are taking the derivative, it's multiplication by a. If we are doing antiderivative, it's multiplication by 1 over a by substitution. These shortcuts come really handy. Again, that's what we did too. You do 1/2. Let the integral go now from 0 to pi/2. Plug pi/2 in. We get 2 sine pi/2 minus 1/2 cosine of pi. 2i of pi/2 is pi. All of that minus plug 0 in. 2 sine 0 minus half cosine 0. Okay, sine of 90 degrees is 1, so we have 2 times 1, 2. Cosine of pi is -1, that makes it a plus 1/2. Minus sine of 0 is 0. Cosine of 0 is 1. Okay, so the value here is 3 for this integral. The actual value is 3. And for sure, 3 should fall between these 2 points, endpoints. Yeah, it does. I mean, 3 is a number between 0 and whatever that is. I don't know the value of that. 3√3, let me see here. Let me calculate 3√3/4. 3 times √3 divided by 4, and then we need to times that by pi. It's 4. Okay, this is about 4. So the value of the integral being 3 is between 0 and 4. Okay. Anyways. So again, shortcuts for those integrals. All right, let's move on to section 3. Let me see what's in 3.2. 3.2 is mean value theorem. You're asked to do 15 and 21. Let's discuss 21 in section 3.2. If you look at the problem, they say it's mainly a conceptual problem. We have a function f of x. It's a rational function. It's given as x minus 3 to the -2 power. So let f of x be that. Show that there is no value of c in the interval from 1 to 4 such that the conclusion of the mean value theorem is satisfied, which says f prime of c is equal to the slope of the line through the endpoints, f of 4 minus f of 1 over 4 minus 1. But you're like, wait a minute, didn't the mean value theorem say there is guaranteed to be a c in the interval? So again, let's say we have some function. At some function from, say, A to B, where we find the slope of the line through the endpoints. Okay, so this is the line going through those. Let me see here. This is the line through the endpoints. Mean value theorem says there's for sure another there's for sure a number between A and B where the tangent line at the point on the graph is parallel to the line through A and B. So right there. Okay. According to this graph, there's a number C, let's say C is right here. That is between A and B where the slope is equal to the slope of that line. That's what mean value theorem guarantees. If the function is continuous on 1 to 4 and differentiable between 1 and 4. And guess what? This function, guys, is not continuous on 1 to 4 because 3, which happens to be inside 1, 4, is gonna mess this up. Okay. So f of x, which you could write as 1 over x minus 3 squared, is not continuous at x equal to 3, which happens to be in the interval of 1 to 4. So mean value theorem does not guarantee the existence of such C. Where the tangent line and that secant line are parallel. Well, let's try to solve this equation. Let's see if we can, if there's actually a C or not. Okay. So what you do is take the derivative. So here we're attempting to find C. By basically solving this equation for C. Okay, we need the derivative, take the derivative, f prime of x. Okay, that's already in power form. It's -2, bring the -2 down. X minus 3 to the power of, take 1 away, -3. Chain rule, don't forget, times the derivative of inside, which is just 1. Okay, so this is equal to -2 divided by x minus 3 cubed. Okay, this is f prime of x. All right, so let's now set this equation up. Okay, f prime is -2 over x minus 3. I'm going to replace x with c, so c minus 3 cubed. Again, this is f prime of c. And we want to know if this is equal to f of 4. F of 4 is you plugging 4 into your function. Okay, which is 1 over 4 minus 3 squared minus f of 1, plug 1 in, divided by 4 minus 1, which is just 3. Okay, so it looks like a pretty ugly equation that you have to solve for C, but it's not. It does look horrible, but it's really not. Because 4 minus 3 is 1. So here we have -2 over c minus 3 cubed equal to 1 minus 1 minus 3 is -2. Square that, you get 4. All divided by 3. Okay, let's do 1 minus 1/4. On the top, we have 3/4 all over 3. Okay, so what we can do with this fraction is to cancel out the 3's. That's 3 divided by 3 to get a much nicer equation. -2 over c minus 3 cubed equal to just 1/4. Okay, so we need to, again, a lot of it was just basic arithmetic. We just need to solve this equation for c. You can cross multiply equal to, yeah, so I multiplied those, multiply -2 and 4, you get -8. And so that times that, those two multiplied. All right, we got to get c. There is a cube, you got a cube root. To get c minus 3 on its own equal to the cube root of -8, which is -2. And then add 3 to solve for c. Okay. And that gives us c equal to 1. Okay. Yeah. So, guys, what does this say about the answer? Show there is no c in the interval 1 to 4. Inside the interval 1 to, we got 1, we got a solution, but the solution is not in this interval, is it? It's not. Between 1 and 4, a 1.1 would be a solution. A 2 would work, a 3 would work, a 3.99 would work, 4 wouldn't, 1 doesn't. Okay, so c equal to 1 is not in the interval 1 to 4. Okay, so mean value theorem did not work. Because again, f is not continuous on closed 1 to 4. If you want to use the mean value theorem, the function has to be continuous on a to b and differentiable on from between a and b. Maybe we'll do a graphing. Oh, I want to do a limit problem where you have the limit at infinity. So section 34, and we'll do problem. You're supposed to do 17 to 20. We'll do 18, I guess. which is the limit as t goes to infinity of t plus 3 divided by 2t squared minus 1. Okay, so the way your book and so many teachers want you to do this problem is by using a lot of algebra, which is factorization of the t squared from within the square root, and then reducing, dividing, and then taking the limit. But I don't want you to do any of that. I just want you to use leading terms, okay? And that's what you were supposed to do on the third exam. A lot of people manage not to do that either. Okay, so I'm trying to make the problems very, very simple, guys. You got to take advantage of it. Yeah, so again, we said that in a long run, t goes to infinity. That means in the long run. Okay, we're going to use the fact that in a long run, a polynomial is going to act like its leading term. Okay, so this is the limit. This is the same as the limit as t goes to infinity of, on the top, just t. If you think about it, we have two lines. T plus 3 is this line. This is t plus 3. And t is this line. It's the line going through the origin. They both have the same end behavior. They both go to infinity, right? They're parallel. They both go to infinity the same way. In the denominator, we have 2t squared and negative 1. 2t squared leads. Okay, reduce that fraction by first evaluating the square root. Square root of, so top stays as is. In the bottom, we have a square root of 2t squared. You could split up the square root. Square root of 2 is just root 2. It's irrational, leave it. Square root of t squared is not t, it's absolute value of t. Okay, absolute value of t means t or negative t, depending on the domain. Okay, as t goes to infinity, suggesting t is positive, absolute value of t is just t. So, as t goes to infinity, of t over root 2 times t. So again, justification is that absolute t is equal to t since t is greater than 0. Okay, if t went to negative infinity, then absolute value of t is negative t. Why do we need the negative t? It's because we need the extra negative, because extra negative factor will multiply t, which is a negative number itself, into a positive. Okay, but here t is positive, t's cancel out. Reduce, you get the limit of a constant. 1 over root 2t is a constant. And we all know that the limit of a constant is the constant. So 1 over root 2 is the limit. Okay. Yep. Guys, questions? Alrighty, then let's do a graphing problem, which should take a good amount of time to accomplish. Section 3.5. Let's see which problem to take. We have 11, 13, 14, 17. Maybe we'll do, let's see here. I don't know. Let's do 13, I guess. Okay, so here our function is f of x is equal to x over x squared minus 4. Guys, I will also give you the derivatives. Let me quickly, guys, calculate the derivative here on Wolfram alpha. Just give me a second, okay? So x. Yeah, good. The first derivative. That looks too good to be let me also calculate the second derivative, because this problem already doesn't seem interesting. Well, yeah, the derivatives are not interesting, guys. So let me find a different function. I don't know why I was never a fan of the functions to graph in this book. That's why I have that graphing packet. Okay, I guess this is a little better. All right, let me change the function to the function in number 17. Which is x minus 1 over x squared. Okay, first derivative, f prime of x is 2x minus 3. I'm sorry, hold on a second. That's the second derivative. Let me get the first derivative. It's 2 minus x, or negative x minus 2 over x cubed. And we also need the second derivative for concavity analysis. So let me get that also. Which is 2 times x minus 3 over x to the 4. And if there are y values that are crazy in value, I'll give you those y values as well. So this is a type of this is a rational function, and on the third exam I did not ask for the graph of a rational function. It was the graph with the cusp. Okay, but this time I'm more likely to give you a rational function to graph. All right, so again, the process is by part A, finding the domain, poles, and vertical asymptotes. This is not too complex of a function. So here domain is all x such that x can't equal to 0. 0 is the only number that makes the denominator 0. And therefore the function undefined. Okay, there is only one location of discontinuity, and it's 0. And this is where the function has a vertical asymptote. It's happening at x equal to 0. It's an infinite discontinuity because when x goes to 0, if you look at this function, as x goes to 0, the denominator gets small. So you divide by something that is getting small, the whole thing goes big. Okay, getting big, meaning that there is a vertical asymptote. This function doesn't have any removable discontinuity. Basically, there are no factors on top and bottom that would cancel out, right? So for example, if we had a x plus 1 on the top and an x plus 1 on the bottom, the limit as x goes to -1 would exist. Although the function is not defined at -1, the limit would exist, which means that there is a removable discontinuity or a hole. A hole, remember, a hole is when top and bottom have a common factor, and this doesn't. All right, so no holes. Because numerator and denominator have no common zeros. If they did, then that 0 would be the location of a hole. Okay, so imagine top and bottom become 0 when x is 2. Then the function has a hole on its graph at 2. And this doesn't, just a vertical asymptote at 0. Part B, intercepts. Okay, for the x-intercepts, you're going to set the function equal to 0. Okay, and the function is again x minus 1 over x squared. Set it equal to 0. A fraction is equal to 0. Guys, can you see the screen, by the way? Are we okay with the no blackouts?
Yep.
Okay, cool. Yeah, so again, guys, remember that a fraction is 0 when the numerator of the fraction is 0, because 0 divided by anything is equal to 0. So if you want to know when something, a fraction is equal to 0, just look at its top. Set the top equal to 0, and that gives you x equal to 1. And that's x-intercept. X-intercept is at 1 for x, 0 for y. Y-intercept is always f at 0. Every function, if it has a y-intercept, there would just be 1. There could be multiple x-intercepts, but a function can't have more than one y-intercept. Because if it has more than one y-intercept, then it wouldn't be a function. So f of 0, again, can't be done because remember that the domain excludes 0. Plugging 0 here makes the function undefined. So this thing does not exist. No y-intercept. C, horizontal asymptote. And horizontal asymptote crossing. We want to know when the function is going to cross its horizontal asymptote. If it does, horizontal asymptote has nothing to do with the domain. The vertical asymptote does. At the vertical asymptote, the function is not continuous. The function is undefined. So the graph of a function can't cross its vertical asymptote. But the horizontal asymptote is something entirely different. It has nothing to do with the domain. The horizontal asymptote is the end behavior. It's the horizontal line that the graph approaches in a long run. And as it approaches, it can intersect that horizontal asymptote many, many times, okay? Again, let's say this is a horizontal asymptote. Graph can intersect it sometimes, but in the long run, it's gonna get close to that asymptote. A horizontal asymptote can be intersected. So how do we find the horizontal asymptote? We take the limit of the function, because we want to know what happens to it in a long run. The function is x over x squared minus 1. Take the leading. On the top, it's x. The leading, the bottom is x squared. X over x squared is 1 over x. And 1 over x is going to go to 0 when x gets big. Okay, so horizontal asymptote is at y equal to 0. Okay, so now we need horizontal asymptote crossing. Okay, again, if there is a horizontal asymptote and the function crosses it, at that crossover, the function and the horizontal asymptote have the same y value. Same y value. So you set them equal. Set f of x equal to the y of your horizontal asymptote. Okay, so again, the function is x over x squared minus 1. Set it equal to 0. That's the horizontal asymptote. And again, we have a fraction that's equal to 0. Look, you can just put this x squared minus 1 in front of 0. You're going to end up with x equal to 0 anyway. Set the top equal to 0. You get x equal to 0. So yeah, and that, remember, that is the that's also the x-intercept. The horizontal asymptote happens to be y equal to 0. This is really the x-axis. The x-axis is also the horizontal asymptote, and therefore the x-intercept is going to be the crossing of the horizontal asymptote. Okay. HA, or graph, crosses the horizontal asymptote at x equal to 0. All right, so that's all the algebraic analysis. Let's do the derivatives analyses. Okay, that would be first derivative. Okay, so let me just copy down the first derivative one more time. F prime is negative x minus 2 over x cubed. Okay, we're gonna find the critical value. Set f prime equal to 0. Okay, and again, guys, just look at it and get the solution. Please don't waste your time writing down information that can be, answers that can be obtained right away. So when this is 0, yeah, and you have a fraction that's 0, the only way it becomes a 0 is when the numerator is 0, which means that x has to be 2. Okay, so this is a critical value because it's in the domain. What does this mean? This means that at x of 2, the function can have a local max or a local min. That's all. All right, now we also set f prime to d and e. Okay, see when the derivative is undefined. Do I have, guys, let me see here. Sorry. This was f of x. No one said anything here. Or did you guys? Did I miss something here? I think I did.
Yeah, you wrote it wrong in C. As you
did,
started
huh?
D, I caught that, and then I was gonna wait until you were done with D.
This, right?
Yeah, even at the top of C when you started taking the limit.
Uh-oh.
The -1 should be on top.
Yeah, x minus 1 should be on top. So it's x minus 1 over x squared. Yes, we'll fix that.
But that changes the horizontal asymptote crossing, doesn't it? Shouldn't it be?
It does change the crossing. It does change the crossing. It doesn't change the horizontal asymptote, but it definitely does change the crossing. We'll fix that quickly. X minus 1 over x squared. So that gives us x equal to 1. Wasn't that the x-intercept? It was the x-intercept. Yes. Okay, so crossing happens at, x-intercept of 1. Alrighty, so that's that. Okay, so let's go back to the derivative. Yeah, derivative is that. Now, derivative is again 0 when x is 2, and it's in the domain. So that is a critical value. F prime does not exist when the bottom is 0, which gives us x equal to 0. This is not in the domain. Because again, if you look at the function has 0 excluded from its domain. So if you try to find a critical value and the number is the same as the exclusion of the domain, then that just can't be a critical value. It's an asymptote. A vertical asymptote can't be a location for local max, local min. Right, guys? The derivative can change at a vertical asymptote. Again, you can go from, if there's a vertical asymptote, we can go from increasing to decreasing after that asymptote. But there is definitely no local max. How could the graph have a local max at that vertical asymptote? So let's check. Let's check the sign of the derivative. All right, locate the zeros of the derivative on the number line, whether it's a critical value or not. Okay, so we have 0 and 2. And I, for myself, indicate here that 0 happens to be a vertical asymptote. All right, you don't have to, but that would kind of help for the future. Okay, let's test the sign of the derivative, which includes negative x minus 2 as factors and x cubed as a factor. Take some test points. Let's say we test -1. Okay, so you put -1 here, you get negative times negative, that's a positive. X cubed -1 cubed is a negative. The overall sign of derivative is negative, telling you that the function is decreasing. Okay, between 0 and 2, you can test 1. All right, here we get negative of 1 minus 2. That is a positive again. 1 cubed is a positive, 2 positives. That would be a positive derivative, suggesting the function is increasing. So a function goes from decreasing to increasing, but again, we just can't say that the function has a minimum at 0. 0 is not a point on the graph, so it can't be a minimum. It's a vertical asymptote, and the derivative is changing sign. Okay, 2, which is a critical value. Let's pick a test point after. We could test, say, 3 or 10. Put 3 here, you get negative of 1, so that's negative. 3 cubed is positive. Derivative is negative. Function is decreasing. So 2 is a local max. Okay. Also find f of 2 because we need to know where the point is on the graph. Put 2 back in the function. 2 minus 1 over 2 squared. That's 1/4. So local max is at 2 and 1/4. No local min. And again, can't say local min is at 0 because we go from decreasing to increasing. 0 is a vertical asymptote, not in the domain. Okay, let's do a second derivative. Analysis. And I'm going to copy down the second derivative function. Okay, so again, just like the first derivative, set f double prime equal to 0. Okay, top 0 gives us x equal 3. And again, this is in the domain. So this could be a possible point of inflection. Possible inflection point. All right. Also see when f double prime does not exist. And again, this happens when the bottom is 0, which gives us x equals 0, not in domain, not in the domain. So this can't be a location for inflection point. It's an asymptote, and again, At an asymptote, the concavity can change. You can go from concave up to concave down. Okay, so let's test on the number line. Okay, again, we have 0 and 3. And again, for myself, we are indicating this is a vertical asymptote. So second derivative factors are 2 times x minus 3 and x to the 4. X to the 4 is always positive. Okay. But let's test negative 1, right? Negative 1 minus 3, negative 1 to the power of 4, positive. Second derivative, therefore, is negative, telling you that the function is concave down. Okay, you can test 1 minus 3, negative again, 1 to the power of 4 is positive. Once again, a negative second derivative. So at that vertical asymptote, the function is still concave down. So if we have a vertical asymptote, then we have concave down, concave down. All right. Test 4. We have positive, positive, concave up. So inflection point for sure, it's happening at 3. Also need f of 3 because it's a point. We need to locate it. Plug 3 back in the function. 3 minus 1 over 3 squared. Which gives us 2/9. Okay, so inflection points at 3 and 2/9. Okay, so no crazy y values here. We don't have any irrational like √3, √5 y values, manageable. Let's draw. Okay, so let's go back to part A. Part A, we have our vertical asymptote only, no holes at x equal to 0. X equal to 0 is the y-axis. Basically, y-axis is acting as an asymptote. All right, part B, we have our intercept. Intercept is happening at 1, 0 only. So graph is crossing the x-axis right there, which also happens to be the crossover of horizontal asymptote at y equals 0, and again, crossover at 1. Y equal to 0, again, is the x-axis. Okay, so this is the horizontal asymptote. And again, we already have the crossing of the horizontal asymptote. All right, now we have local max at 2 1/4. All right, let's say 1 is here. So 2 1/4, maybe I'll make 1 here. 2 1/4 would be there, we said max, right? That's max. So draw a bump right there. That's the max, local max. Already? Yes. So we know our graph is decreasing before the asymptote. Yeah, so from here to here, it's always going to decrease. And what do we also find out? We find out that from the asymptote to that local max, it's going to increase. And then from the local max to infinity, it's going to decrease. Okay, so just keep that in mind. We also have our inflection point, which is again happening at 3 2/9. 3 2/9. So 2/9 is pretty small. Let's just say it is here. Okay, point of inflection. Already? Yeah, and I have the concavity information right in front of us. So let's go ahead and draw. All right, so before the vertical asymptote, we have thankfully no intercepts, right? No intercepts, nothing significant is going on. Okay, and we just know that the function is decreasing concave down. There are only two ways, regardless of the derivative and the concavity, there are two ways that you could have drawn the graph before the asymptote. Okay. Since we have a horizontal asymptote and a vertical asymptote, the graph could only be done like this or like this. It's one of those two. Graph can't look like anything else. Remember that asymptotes they act as boundaries, right? So I mean, I can't have a graph like that. You can't just draw random stuff here. Graph has to get close to these asymptotes. Okay, so it could do that, or it could do this. You could have this branch or this branch, nothing else. So which one of them? We know it's decreasing and it's concave down. So it has to be this right here. That's concave down and it's rolling down, it's decreasing. Okay. I can't, again, guys, I can't do random stuff. I can't cross that the x-axis. I can't go back down, change direction. We just can't. This is a decreasing, always concave down, always graph, and it's getting close to those asymptotes. All right, from 0 to 2, from 0 to 2 over this interval, it is going to increase and it's going to concave down. So again, we're coming from near the asymptote, increasing while being concave down. We have to cross the x-intercept, go towards the local max. Okay, once we hit that local max, we have to change trend to decreasing while being still concave down. We still are concave down until we hit 3. So it's like a parabola, a downward parabola, changing from increasing to decreasing while being concave down. Right? It's going to be decreasing forever, but after 3, it's going to go concave up. Okay. So again, concave down, sad face. Right there, it becomes happy as it's decreasing forever. Okay. Let me just fix that. All right. So again, increasing, decreasing, right? Increasing concave down, decreasing concave down, decreasing concave up. Concavity is changing at that point. And remember that we can't go below that asymptote ever again. The graph is going to just keep getting closer to that horizontal asymptote, but not go below ever. Because the only crossing of the x-axis is right there. No more crossings ever again. Yeah, so I will do an optimization, guys, and then that'll be it pretty much. Do you guys have any optimization in mind that you want me to do? Guys, Allison, Audra, Darren, guys, do you want me to do a certain optimization from that list from section 3.7? Well, I don't know why it's marked 3.6. That should be 3.7. Oof. So it says should say 3.7. I have it as 3.6. I'll email everyone. So problem, we have 5, 8, 15, 19. We have 25. Looks also good. 27. We have 37. 37 is the right circular cylinder that is in a sphere of radius r, and you want the largest volume. What do you guys like me to do?
That one's fine.
Which one? The
volume one.
Sphere? Okay.
37.
Okay, let's do that then. So we want to maximize. Yeah, we want the volume of the largest cylinder in a sphere of radius. Let me write that as capital R, because lowercase letters are typically used for variables. Here R is a constant. For example, R could be 10. Find the volume of the biggest cylinder in a sphere of radius, let's say 10. Okay, in this case, they want the radius to be left as R. Okay, so we definitely want to draw a picture here. The constraint is the sphere. You can't go beyond the sphere, guys. Okay, and we have a cylinder in there. Oh. Let's see. Okay, so here is such a cylinder. There are so many cylinders that can be inscribed in the sphere. There can be infinitely many cylinders that are inscribed in a sphere. Okay, this is one. I could draw the picture like that. I could draw the picture like that. I could draw it like this. And every one of those cylinders have a volume. Okay, one of them has the largest volume. For instance, if I draw the cylinder like that, pretty narrow, a cylinder with a small radius is going to have a small volume, right? So the lower the radius of the cylinder, the lower the volume. The lower the height of the cylinder, if I choose the height tiny, then the volume is not going to be too big. It's going to get small. So we want to know how to choose the dimensions, like what should the radius be? Okay, here is the radius of the cylinder. What should the height be? We want to choose. We want to find little r and little h that maximize the volume of the cylinder. Okay, the dimensions. So step one is to draw the picture, and we did. Okay, step two is to write down the objective function. The objective function is to maximize, again, the volume. If it's a volume, area, distance, whatever formula that you need, you'll be given volume of a cylinder is pi r squared times h. Okay. Yeah, pi r squared h. So now the thing is that, again, this is a function of r and h. We want to take the derivative, set it equals 0. We want it to be in terms of only one variable. And that's where you have to use the constraint. The constraint, again, is the limitation in the problem, which is the sphere. So again, this object can't go beyond the sphere of radius capital R. Okay, so draw the radius of the sphere. And again, I talked about this in class. You want to draw the radius. Look, there are so many ways that you can draw the radius. You can draw the radius like that, right? You could draw the radius like that. You can draw the radius like that. Draw it in a way that it forms a triangle. Okay? Draw the radius of the sphere so that you could see at least a right triangle, because if you have a right triangle, you can use Pythagorean theorem. Okay, so I'm going to draw the radius of the sphere going from center, like, let's say like that. Or you could draw it like that, or like those. Because right there, guys, we have a right triangle. Okay, let me draw it this. Look, guys, it really doesn't matter how you draw it. But I could draw it like that also. Okay, we have a right triangle here. The radius is capital R. Don't confuse the capital R with little r. Little r is the radius of the cylinder. Capital R, the sphere. Okay, we have a Pythagorean relationship between little r, capital R, and H. Guys, that relationship equation is going to help you eliminate either R or H. Okay, so let me draw the triangle out here. Capital R, little r. All right, now we need to know the length of this length right here. Let's see. Yeah, guys. So what about the length of this length of the triangle?
H divided by 2.
H over 2 works. Yes. Very good. H over 2, perfect. Yeah. This is the same as that. I mean, we have symmetry here. Okay, so write down the relationship. Here we have H over 2 squared plus little r squared equal to capital R squared. Remember that capital R is a number. It's a known given value. It's not a variable. It's not something you're trying to find. It's given. All right, so we can take this relation and solve it. You could solve it either for H or you could solve it for R squared, guys. You could solve this for R squared and plug it for R squared here. Yeah, R squared is equal to capital R squared minus H squared over 4. Okay, so now we're going to plug this into the objective function, which is V equal to pi capital R, not capital, just little r squared times H. To get V equal to pi times capital R squared minus H squared over 4 divided by, or times by H. Okay, so again, what I did is that I took this R squared and replaced it with this right here. Because now, look at that function. This function is only in terms of H. We have only one unknown H. And again, capital R is given. And it is a third degree, it's a third degree polynomial. We have H squared times H cubed, which represents volume. Okay, so step 4. We want to maximize V, which is a function of H, and I'm going to write that as negative H cubed over 4. Distribute H in and write it in a descending order if you want. Plus R squared times H. Okay. And don't forget the domain. The domain is, the variable here is h, and h goes from 0 to 2r, guys. Right? The largest h can get is the same as the diameter of the sphere. We have r here, so h, highest h is 2 capital R.
Should we still have pi in there?
Should you what?
Still have pi in the equation.
Oh, did I drop pi? I did drop pi. Thank you. Yeah, so let's put pi in front of the whole thing. It's just a constant. When you take the derivative of that constant factor is just itself. It's gonna stay in front. And when you set it equal to 0, it gets divided out. So if you drop pi for whatever reason, the final answer is not going to be incorrect. Okay, so take the derivative v prime of h, keep the pi in front, take the derivative of h cubed, you get negative 3h squared over 4. Please don't use quotient rule. 4 here is just a constant. Plus the derivative of r squared h, guys, remember that the variable is h, it's not r. This is just a number, okay? This is like 100. The derivative of 100h is 100. The derivative of h is 1, so we get r squared only. Okay, that's the derivative, set it equal to 0. And solve this for h. Hopefully that's your critical value. Pi again is just a constant factor. You can zero it out. Okay, the only time this is 0 is when this factor is equal to 0. Move the r squared over. You get 3 over 4h squared equal to r squared, right? The negative just cancels out. Multiply by 4/3 to solve for h squared. So h squared is 4/3 capital R squared. Whatever r is, take the square root. We do square root to get h equal to, you don't need a plus or minus because we're talking about length. Okay, h is root of 4, 2, root of 3, root 3, and root of r squared is r again. Don't do absolute value or plus or minus because r is just positive. That's our critical value, guys. This is the critical value because it is in the domain. Okay, 2 over root 3r is between 0 and 2r. It is the critical value. Okay, and it happens to give us the absolute maximum, because if you plug 0 and 2r into the volume function, you get 0, and this plugged in will give you a positive value. Okay, yeah, so let's just do it. Part 5. Okay, so again, on 0 to 2 capital R with critical value h equal to 2 over root 3r. V at 0 is 0. Don't bother plugging that in. And again, this is our volume function, right? If you plug 0 for h, you just get 0. Plug 2 over root 3 r in, we get pi times negative When you plug 2 into H, you get 2 cubed. That would be 8 over. When you plug root 3 into H, you cube it, you get 3 root 3. Or you could write it as root 27 if you want. All of that divided by 4 plus, yeah, and don't forget there's an r cubed. Also, so plug r into H, you get r cubed. Plus we have r squared times H, and again, H is 2 over root 3 r. This is the volume at that critical value. Let's reduce and add. Okay, so here 4 and 8 reduce. That becomes a 2. We get negative 2 over 3 root 3 r cubed minus 2 over root 3 r squared. R is r cubed. That should be a plus. And just add these two. If you want to add these, this is a 3 root 3. That is a root 3. All you have to do is multiply this fraction by 3 over 3. That would be a 6 over 3 root 3 r cubed. So almost done. You have negative 2 plus 6, that's a 4. Okay, so we have 4 over 3 root 3 r cubed pi. That's the volume. Okay, that's the actual volume. And again, if you do v at 2r, which is the right endpoint of the domain, you just get 0. Okay, and that's it. So not only we found the height, we also found the volume, which I'm not likely to ask you. I might just ask you to find a dimension. Already?
How
Yeah.
did you get the 8r cubed, like the bottom part, like the 3 times root 3? I'm just a little confused on that.
For this one?
Yeah, that
Yeah.
part.
Yeah, I got you. So
Thank
when you plug root 3 into H and you cube it, right? Let me show you. You have 2 over root 3 r. If you cube that, 2 cubed is 8. Now root 3 cubed is what? It's root 3, root 3, root 3, isn't it?
Yeah.
So 2 root 3s, that's a 3. And you get
Oh,
yeah.
gotcha. So they cancel out the root. Okay.
Right.
Okay. Gotcha. Thank you.
Mhm. Yeah, so guys, that would be, I guess, it. Then the rest is just chapter 4 and 5, which are pretty recent stuff. Make sure you guys know your trig sub. No, I'm sorry, not trig sub. U substitution when you're doing a integral. And if you have time, go over the last review for exam 4. All right. And that's it.
How many questions are on the exam?
Oh, let me see. Frankly, I don't know yet. Let me see here. I don't want to tell you something and do something else. But let me just check. So I would say somewhere around 15 questions. some of them have multiple parts, like I could ask you a area question followed by volume for the same region, for example. You know, or you could have a question where you take the derivative of a couple of functions, a question where you take antiderivative of 3 or 4 functions. So yeah, 15 I would say altogether, and some have multiple parts. Okay.
And it's at 8 a.m. in our classroom?
Yes. Yeah.
Thank you.
What would be the like
Okay.
biggest focus on the exam, by the way? Like what unit or subject?
I don't know. Biggest
All right.
focus. Biggest focus. What do you mean by that? What do you mean? So we're gonna have a question for sure from area 1 question, of at least 1 question from volume, where you have to rotate the region around a horizontal axis and a vertical axis. Okay, you're gonna have a using the washer method, you're gonna have a volume question on just 1 volume question on the cylindrical method, right? What else? So that stuff you'll be asked for sure. You know what? I really can't tell. That's just equally, the exam is equally distributed among everything I did and you know, during the review, like these past
All right.
days. Yeah,
Got you.
I
Just
can't
like
say I can't
equally
say-
review everything.
Pretty much, yeah. Like I would definitely go over all problems that I did, you know, today and last time.
Okay.
Mhm.
Are you available like tomorrow? Is there like an office hours or anything if you would have any questions?
I don't have office hours, but you can stop by to pick up your exam tomorrow.
To pick up the exam?
Yeah.
Oh,
Mm,
for us to pick up the exam.
Yep.
Okay.
I'll be there from 11:30 till 11:20 till maybe 1.
And you can send us those exam 3 solutions that you took down?
Yeah, so again, yeah, I'll try to. There's just a couple of students who haven't taken the exam because they had COVID, so I just want to see what's going on with them. If I don't hear from them, I'll post them soon. If not, I will email it to you. Should just stop the video here.